Okay, sir.
Sir,
Yes.
sir, I have a general question, sir. So, sir, the layout which we have made below was for A bar B, right, sir? Yeah, for this
AB
one
bar,
below.
NAND gate.
Yes, sir. Okay. So, sir, my doubt is that when we consider a chip or something, sir. So, if how does that know the how many standard cells should I make of this kind?
You write an RTL?
No, sir. I'm
Okay. You
RTL.
made the schematic.
Okay.
You made a
Okay.
schematic.
RTL. Yes, sir. Yes, sir. Yes, sir.
No? So the schematic you will tell I want a NAND gate.
Yes, that will tell, sir. But so like this, many number of cells are present, right, sir?
Yeah.
In,
So see, that was why we covered that VDF pura design flow, na?
Yes, sir.
What did we say? We will write the RTL, we will simulate it, we will see the functionality is correct. Then we will go to the synthesis stage. In
yes,
that
sir.
synthesis stage, I will get to know how many NAND gates.
Okay. So it's predefined.
So you cannot forget any of the lectures till now.
Okay. Okay, sir.
However fluffy they might sound to you, you cannot forget any one of them.
Okay, sir.
They are the basis, they are the foundation. That is the basic understanding on which we are building all this now.
Yes, sir. I do understand. My doubt is that whenever we write a RTL, sir. So my doubt is that all this is supposed to get into a chip, right, sir? Finally, at the end of the task, it's supposed to be it's supposed to be written into the. It's supposed to be configured on the chip. So RTL which we write is it's before that, right, sir? So
yeah.
So how even in RTL we just write a code, that's it. What I have seen, we just write a code. I'm like, how is the hardware? I'm like, how does that decide key? Okay, I need this many number of NAND gates, I need this many number of NAND, but we write only one line over there, sir.
Yeah, see, you write one line, but there are 10 gates that are introduced because of that line.
I'm like, how is it? I'm like, how is it making relevant?
This step is called synthesis.
Okay, okay, sir.
This step is called synthesis. So if you simulate a Verilog and tell me that I know Verilog, I will not pay any heed to what you have told me. Unless you tell me I know how to write Verilog and I have synthesized Verilog into 100 gate designs, 500 gate designs, or 1 million gate designs, then I will know, okay, how complex Verilog you can write.
Okay, okay, sir. Understood. Thank you, sir.
Okay, otherwise Verilog is simple C language.
Yes, sir. Yes, sir.
But we call it hardware description language. Why?
Like, because we are making hardware out of that.
Yes, and that first step of converting that C English language into something which is closer to VLSI is synthesis.
Okay, sir. Thank you, sir.
So till now, the undergrads have done in ELD. We have done Verilog in ELD. So we were focusing mainly on FPGAs. So we did not much so we wrote mostly behavioral codes, behavioral descriptions, and we did not think that how many AND gates will it use or how many OR gates will it use.
No, but ELD maybe you must have seen, this many lookup tables are used, this much has been used. You must have looked at the resources that are getting used.
Yes, so that we have.
So you were looking at that.
Yes, sir.
Each register entry in the lookup table represents some gate. You can assume that.
Yes. Yes, sir. One lookup table can be converted into an equivalent combinator.
Yes, exactly. So you're already looking at that. You just not realize that this is actually going on silicon also like this.
Okay, sir. So I mean, sir, so this is the first time that I am thinking about that. I never thought about reducing the resource utilization to an extent as to think about AND gates and OR gates.
So now you know.
I don't even know, sir. If we can do that using behavioral.
Yes, you can do that.
So, but the AND gates and OR gates are converted.
No. See where you put the for loops. For loop all at once can be considered as parallelism.
So generate for loops or combinatorial for loops?
Whichever.
Because generates will create instances and.
Yes. So that is parallelism.
Yes, sir.
So if you do not put for loops for parts which do not need to be put in parallel or do not need to be replicated, you can save area.
Okay, sir.
It may increase time to execute the entire instruction, yes, but you will save area.
Yes, sir. Yes, sir. That is, yes, sir. Instance at this, we can save area at the instance level,
Yes.
module level area we can say. But let us say that I need an adder. I just write a single line of Verilog code, C equals to A plus B. So now I have no control over how many transistors will be.
Yes. Now the FPGA, which FPGA board you are using, that will define which adder is being used. Yes.
Yes, sir. So what do we do in silicon, in ASIC design? What do we do?
So we'll come. We'll towards the end of this course, we'll talk about different kinds of adders also. Don't worry.
Okay, sir.
So there are different kinds of adders. Some would have lesser area, some would have lesser delay, some would have lesser race conditions.
Look
So we will
ahead.
look into that.
Yes, sir.
Yeah,
Look.
carry look ahead adder, ripple carry adders, all those things we will see. We'll not go into too much detail because that is simple combinatorial logic. You can always get it. See, this information you will not get in the books. आप कितनी भी books छान लें, आपको ये information नहीं मिलेगी. So my intent is I give you this kind of information in the class. Unfortunately, out of 93 students, only 35 are attending the class today. So I am here to offer and to give you additional information and answer your queries, but you have to be here to ask those questions.
Okay, sir.
So my question was, where is the strap now? We not made the strap here. So where does the strap come? Where do we make the tap for the P well and the N well to prevent latch up?
Sir, at the end of that DRC length, 30.
Yeah. So what we say is that if this wall, the wall that I had made, if this wall is 30 microns, so I will simply make taps at the boundary of this wall. Okay. Or usually my walls would be thousands of microns wide. So what do? I say that, okay, these are my rows. In these, I will put taps at regular intervals. You've seen pillars in flyovers? So those pillars come after regular intervals, nahin? So these taps you make after regular intervals so that no point has a tap which is farther than DRC distance away.
Sir,
Yes.
sir, DRC, so this one cell that in particular wall is basically a standard cell, right?
No. I'm not. I've just shown you rows now. The standard cells in this would be very small ones.
So what
the
is
vertical
this one?
ones that I have shown in this view are the taps. I should have probably used a different color. Let me use a different
Actually, so this basically this different kind of, for example, say I take a one layer only, and these different blocks, they are basically one standard cells, right?
No, a standard cell, for example, in this, there could be a buffer here. There could be a flip-flop.
So actually,
here.
it's not visible. So can you move to the different side because
Yeah.
that.
Is it visible now?
Yes, sir. Yes, sir.
So there could be a buffer here. There could be a flip-flop here. There could be an inverter here. There could be AOI here. So there are so many cells here. These dark blue ones that I made, they are taps. So that is what I'm saying. The spacing between these taps, मैंने यहाँ पे yellow में दिखाना शुरू कर दिया था. The spacing between these taps, अरे यार, is such that so this was a tap, this was a tap. So the spacing is such that no active region can be there which has a distance of more than 30 micron from the closest tap.
So which active region, sir?
In each of these cells there is some active, na?
Yes, sir. Yeah.
So each active will have some tap within 30 microns of it.
So, sir, this basically the standard cell, this topology, basically we are showing you're showing the standard cell rows here, right?
Yeah, I'm showing you a a 1000 meter top level view of Earth, let us say.
Yeah.
Okay?
Yes.
As you come closer, you will see that the standard cell has these active regions in it.
Yes, sir.
But you will see them only when you come closer. अभी इतनी दूर से आपको खाली ये दिख रहा है कि there are taps and there are these cells. So there are
Yes.
these small cells there. आपको खाली घरों की boundaries दिख रही हैं. But as you come closer, you will be able to see, even identify the cars that are parked outside the house.
Yes, sir.
You've seen Google Maps, na? Satellite maps in Google.
Yeah, yes, sir. So
Yeah,
my
yeah.
question is also this, that for example, these are standard cell rows, right? And for example, once I have placed the standard cells in these different rows, then I'm doing the tapping thing.
Yes, you can do that, or you can actually fixate the taps first and then place the standard cells in there.
So because right when we are doing it, so this was basically we are doing in placement. So after placement, the tapping will be done. You're saying?
Yes. During the placement, taps will also be placed.
Okay, after I place those in the standard cell rows. So, but like in the layout, we are doing with each kind of.
So yeah,
that is
for
confusing.
every cell you will not make a tap now.
Okay.
So in this cell, you're not making any tap. Have you made any tap? Have I shown any tap over here?
No, sir.
Hello?
Okay.
Because I am saying that at the system level, I am taking care of it. You don't bother about it at the cell level. Let us save area.
Okay. So basically tapping thing happens automatically by the tool itself.
So you will have to make a standard cell which is tap type. So you'll have to make a standard cell जिसमें tap बना होगा, tap functionality होगी, and the tool will place those taps at regular intervals.
Yeah. So but that standard cell I will get in the library format, right?
So you will make that.
Okay, those libraries. Okay.
Just like you're making this NAND gate or something over here, similarly, you will make this tap cell also.
So, sir, this active, so for example, in this only this in which you have shown the 12 track, the height one, this diagram only. So the tapping the 30 micron is basically the distance between the, for example, the active of this NMOS and this tapping. So for example, like it happens here. For example,
so
if you
let us
do
say
that, can you
this
show
active,
here?
so this active,
Yeah.
the tap could be 10 cells away.
Okay.
The tap, the substrate connection for this NMOS could be 10 cells away.
Okay.
And it is still fine because it meets my DRC requirements.
Okay, fine. But that has to happen for every active and inactive for every
Yes.
cell. Yeah.
For no active, should the tap be farther than the DRC distance away.
Okay. Okay.
Okay.
So I have one question.
Sir,
Regarding
So there is
this.
still one question which is pending as of now, the question from which we started.
yes,
But
sir.
yeah, ask the question, Animesh.
So there's so there one row is consisting of many standard cells, right?
One row, yes, one row has many standard cells in it, yes.
And those standard cells may consist of an entire unit like a flip-flop or an adder, something like that.
Yes.
So this one row can have many sub-rows of NMOS and PMOS. Is it something like that, or one row can have only one row, one series of PMOS and NMOS?
No, you can have another NMOS right here below it. Provided you're meeting all the DRCs, you can have multiple rows of NMOSs.
Okay, sir. And
Sir, you have to meet the DRC. You cannot violate the height.
Okay, sir. And sir, how are these rows separated from each other?
They are not separated. They are abutting. That is where you will share the metals, na? That is where this VDD will be shared with the cell which is flipped and put on the top. You see this? हमने यहाँ पे दिखाया था. यहाँ पे हमने ये बात करी थी ना, that there is this VDD, then GND, then VDD, then GND. So the boundaries of these carry VDD and GND. And they are shared across the top row and the bottom row.
Okay, sir.
Okay.
Sir, between two tabs, there would be many standard cells. So, sir, in that way, I have to share the NVEL for that many number of standard cell also.
Yes, NVEL. So the template would be such that this NVEL will continue from the left to the right. This NVEL will continue from left to the right.
So sir, that is why it is not advised to make NP and PP parallel to each other vertically, right?
Yes. अब समझ में आ गया तुम्हें, है ना?
जी sir.
Animesh?
Sir,
So
waiting
now
for
I
the
also
question.
want the answer to my
Already
question, the first question. Where should
Yes, sir.
the drain, which should be connected to output and which should be connected to VDD? Yeah, Animesh, please, sorry.
So I was asking the same question.
Achha, you're asking the same question. You don't have an answer yet.
No, still not, sir.
Okay. Devjit?
Sir, I actually had one question that suppose the length of the row is 3 times the size of the DRC for minimum length from where the strap is to be kept. So if it is 2 times the DRC, then we can keep at two ends. But if it is 3 times, then in that case, what is done?
You will put two straps, like you will, how do we do it? I will show you. So if the total length is 3x, so what you will do? You will put a strap here. You will put a strap here. X. In fact, this can be x by 2, 2x, and x by 2.
Okay.
Something like
so
that.
Between two rows, somehow we have to adjust the.
Between two rows, within a row, you will put it.
Okay.
So what is this strap he's talking about, Devji?
The N plus and P plus connections for the substrate. Taps are also called straps.
Okay, right.
Multiple names. So see, we are all out to confuse you.
Yeah.
We are all out to confuse you. So it's okay. Don't worry. Ask if you get confused.
So
that is why it's important to attend the class.
Yeah. So before going to the answer of the question, I also wanted to ask that till now, when you started the original question, the only factor I was thinking about of the diffusion capacitance, right? But for example, in the MOSFET capacitance, when we're modeling it, we sort of three kind of capacitance. One was that it's from the gate to the either source or the drain, one from the gate to the channel, and one from the diffusion capacitance. So why we are not considering the gate to the channel capacitance or other two capacitance also, right?
So Raghav, कर तो रहे हैं. यहाँ देखो.
So one
when we were comparing, when we were comparing this topology with this one, original one that I had made, what did we say? We counted the number of gate to contact capacitances. We counted all the capacitances there.
Yeah.
सब तो कर रहे हैं.
Yes, sir. So, but actually, so one thing. So we have not talked about this gate to the channel one in any mention. Yeah.
Gate to channel तो देखो, gate to channel तो gate region जितनी WL है उस पर डिपेंड करेगा ही ना. उसको आप कैसे कम कर सकते हो? Gate to channel capacitance तो वही रहेगी. Gate की capacitance, gate to channel capacitance आप कैसे कम कर सकते हो? वो तो जितना बड़ा आपने डिवाइस बना दिया उतना बड़ा ही चाहिए. लेआउट में आप थोड़ा ना डिसाइड कर सकते हो I will reduce my device size.
Okay, so that is basically controlled by the specification that someone has given.
Yeah, that is designer. That as a designer, you saw that you want a 5 micron device or a 7 micron device. How can at the layout stage you change that requirement?
So, sir, as of now, I can see that as a designer, the most important that I control is the active region and the contacts. If I can share it, I can reduce the contacts. If I share it, we can reduce the diffusion capacitance. But only the active region I'm considering it. For example, that is only the thing that we are focusing on, like most of the time to control that. Okay. And within this active region, the diffusion capacitance is the most important. That's why we're focusing on that. It seems to me, right?
Yeah.
Okay, sir.
So now tell me, this is my NAND gate वाले two devices. ऊपर PMOSes हैं, नीचे NMOSes हैं. So which one should be ground? Which one should be? So this is since we're just making a stick diagram corresponding to this one. So this is ground. So I make a wire to ground over here, connected to ground. And this is my output. No, ulta, sorry. This is my ground because B connects to ground. And this is my output. Now, where should this metal one go? Should it go to this one or should it go to the boundary ones?
Sir, middle one, sir.
Why?
Sir, because, sir, that's obvious, right, sir? If we give to the leftmost connection, then we won't consider this rightmost
No, we saw now, we can connect it like this. So if I take it to this one, I will take the metal one and do it like this.
Yes, sir. We can.
I can do it. It is not obvious. It is not obvious because of that reason, what you are telling me. It could be obvious because of some
Sir,
other reason.
The
So,
side
from
wall.
my standard cell, I do not want two VDD coming out.
why?
I mean, from the standard cell I design, so I have to attach to the railing that VDD going above there.
Yeah, so I could make two connections. What's the big deal? So if I say that, this is my output, then this will go to VDD, this will go to VDD. What's the big deal? There is a metal running here. What's the big deal of that?
So the side wall capacitance would play a role over here because we need to connect the input to the contact that is between the two gates.
Okay, so you're saying this is how you should make it.
Yes, sir.
Is everyone in agreement with this?
Yes, sir. I'm like, I do.
Sir,
So what happens? Yeah.
Can we? I also think about signal integrity here, because this metal one is crossing P poly 2 times there, and here we can also do it 1 time also.
Okay, so what is it that you really want? Anyways, see, what are these poly? This is signal A, this is signal B. This is out. So anyway, even if you look at the schematic over here, if you look at the schematic over there, you will see there is some coupling capacitance between B and out. There is already something there.
Yes.
Why is there something? You tell me. Because A and out, there is this drain capacitance, there is this contact to poly capacitance, everything is already there.
Yes, sir.
So आप कह रहे हो poly के ऊपर से एक बार extra गुजर गया, that will add some capacitance. I'm not saying it will not add any capacitance. So there is already so much capacitance that A and Y already have.
Right, sir.
So what's the big deal? If you use this as the output, what happens? Output capacitance reduces. If you were using this as the output, there would be extra drain and source capacitance that you would have to bear. अभी आप 20 femtofarad के load पे परेशान हो रहे हो, you are adding more capacitance on the load then.
So addition is due to the side wall only that.
Yes, not just side wall. We also did the calculation on the area, na?
So, but area you said we are taking to be like the same.
No, we calculated that this one would be 140 nanometer extension. This one would be 140 nanometer extension. So total extension will be 280. 280 nanometer into WP. Over here, the central area would be 160 into WP. We calculated this, na? We started with the assumption, but I then gave you the exact calculation. There is so less.
Okay, so we are considering two things, that one after the sharing of the active regions, then we are placing it between. So to reduce that.
Yes.
Okay, right.
See, again, in the lecture we progress. I start with an assumption, but then I clarified that assumption is invalid. In fact, when you do sharing, you save area. And when you save area, you are also sharing source and drain capacitances. You're saving on that also.
So source and drain is a diffusion one, right?
Yes.
Yeah.
Okay. So we have the answer to the first question where we started from, and we did not even open one slide today.